Okay, let's start talking about operationalization. Operationalization is the counterpart of conceptualization. Conceptualization, as the textbook chapter defined, is the process of clarifying the meaning of a concept or a construct. So, for example, in my paper on parasite stress and in-group and out-group trust, I define in-group trust as trust based on familiarity due to kinship, friendship, and geographic proximity, um, drawing on previous scholars' definition. So this is to clarify the meaning of a particular, I would say, construct in this case, because in daily life, people don't really talk about trust as as in-group oriented or out-group oriented. So this notion is purely invented for scientific purposes. So I call it a construct. But anyway, it's not enough to just have a good conceptualization or conceptual definition of the key concepts here. We also need to, for the purpose of empirical observation, operationalize the key concepts and this process, right, to clarify the observational categories or values representing the concept or construct is called operationalization, as defined in the book chapter I assigned to you for this week. Essentially, when we say we're operationalizing a variable, a concept, we're saying, well, we're asking ourselves, or we're answering this question from the readers, how to measure that particular concept or construct. So in this case, having defined in-group trust conceptually, my next task is to make a decision on how to measure in-group trust. So in my paper, again, drawing on previous research, I decided that I will use the following three questions to measure in-group trust. First question, how much do you trust family members? Second question, how much do you trust neighbors? And third, how much do you trust people you know personally? And for each question, I provided a scale, a 4-point scale, um, ranging from 1, do not trust at all a particular type of people, to trust that type of people completely. Um, so that's essentially an operational definition of in-group trust, right? So that's how the instrument you use to um, define this particular concept or construct. Um, in this particular case, we say that each question is an item or an indicator as defined in the book chapter. You can say it's an item, you can say it's indicator, it doesn't matter. People understand you. And then collectively, the three items, 1, 2, 3, right? This is one item, a second item, a third item. So collectively, the three items or indicators, they form a scale or an index or a composite measure of the construct in-group trust. And because it is really based on how respondents, right, survey respondents answer these questions, so these scales are essentially self-reported scales. So we can say that this measure of in-group trust is a self-report measure. Again, this is defined in the textbook. So by the way, the chapter did a fantastic job defining uh, the many key concepts you should know about research methodology. So I will highlight some of them in my lecture slides. Try to provide more examples to help you understand all those important concepts. So please do read the chapter. and all the chapters that assign. Another key concepts I used in my paper is parasite stress. Essentially, parasite stress, operationally speaking, is the prevalence of contagious diseases and their severity, right? How serious they are and how widespread they are. So I obtained, well, I actually, obviously, I cannot just go to the field and go to all those countries and measure disease prevalence myself, right? That's impossible and way too dangerous. So what I did is I went to some very good resources on the internet, in this case called Global Infectious Diseases and Epidemiology Network. And I accessed that network in June 2015. So from this network, from this website, I obtained their prevalence scores of 161 contagious diseases. So similarly, I would not have the time, expertise, um, and courage, perhaps, to actually go to all those countries and measure disease severity. So this time, or in this case, I rely on the report from the World Health Organization. They have a measure of the so-called age standardized disability adjusted life year. It's a mouthful, but essentially saying, well, they're measuring a gap, right, between a perfectly healthy person that would be the ideal, right? Sort of a life expectancy for that person, and then they will measure, how soon this person will die due to all the diseases in the country where this person lives in. So that gap between the ideal life expectancy and the expected life expectancy due to diseases is a measure of severity. So in this case, both sources of measures are what we call archival data. Again, this is mentioned in the chapter. So archival data are essentially existing recorded information, and they're perfectly legit for the use of scientific research as long as the source is reliable, right? For example, World Health Organization, it cannot be more, well, it cannot, this is probably one of the most reliable sources regarding diseases. So it's perfectly okay, right, to use secondhand or archival data to produce some interesting research projects. But anyway, so here I'm highlighting different sources of measures, right? This case is archival data. Previously, it's self-report data. So a key component of operationalization is measurement, because operationalization is the process of making the decision of how to measure concepts, right? So as the chapter defined, measurement is the activity of assigning numerical values to objects, such as concepts of variables, according to certain rules. And one of the most important rules is that there are levels of measurement, not just measure. And from low to high, we can have 4 levels of them: nominal measures, ordinal measures, interval measures, and ratio measures. So at the lowest level, we have nominal measures. As the chapter said, nominal measures, well, when we use nominal measures to measure a concept, essentially we're classifying all the cases or observations, or subjects, participants, into categories. So for example, we have a sample of respondents, and we apply this nominal measure to that sample of participants so that we can sort or classify that sample of participants into one category or the other category, right? So that's how nominal measures work. The chapter mentioned that nominal measures must be exhaustive and mutually exclusive. I think these 2 points are rather straightforward to understand, so I will not elaborate here. So if you have questions, read the chapter, and if still don't understand these two principles, um, do ask me. Um, in practice, we often assign numbers to the labels of categories. For example, sometimes we'll say, well, let's assign 0 to male and assign 1 to female, so that we know that 0 represents male and a 1 represents female. First thing we should know that the assignment of these values is completely arbitrary. We can use 1 to indicate male and 0 to indicate female, and there are no reason why not to do that. Sometimes there are statistical reasons to assign 0 to a particular category, but that decision has nothing to do with determining which category is more of something and which category is less of something, right? It's the purpose of assigning values is not this. Um, as I just said, well, in previous lectures, you will see there are many advantages to assign numbers to categories. One of the advantages is no statistical packages, including R, can compute a mean, or can compute, for example, correlation using string letters, right? Correlations, for example, can only compute it using numerical values. So that's why. Anyway, that's a topic for future classes. The second, well, if we move up the ladder of measurement, we have ordinal measures. Ordinal measures takes a step forward. So if you use an ordinal measure to measure a concept, you're not just classifying cases or observations into categories, but you also rank them, right? So for example, education level. At least when you use this scale, you're treating education level as an ordinal measure, and we'll soon see why. So for example, this scale says, well, if a person did not finish high school, give that person a 1. If a person finished high school, give that person a 2. If the person obtained a bachelor's degree, give him or her a 3. Finally, if the person obtained any graduate degree, a master's degree, an MD, a JD, or a PhD, give that person a 4. Okay. So, and well, sorry, another typo, too many typos, apologies. An ordinal measure can certainly differentiate different categories, right? So we have one category, a second category, third category, and fourth category. So in this sense, ordinal measures function exactly like nominal measures. But as we said, nominal measures do not indicate ranking, right? So there's doesn't make sense that to say that male is of a different rank than female. They're of the same rank. They're just different, right? But obviously these categories they form a rank, they form a ladder, right? So 1 is obviously lower and 4 is obviously higher, right? So there's ranking here. However, ordinal measures do not inform the degree of differences between ranked categories. What does it mean? Well, let's say we have in our sample 5 individuals: Andrew, Brian, Kathy, Doug, and Emily. And here we have their respective education level. So Andrew finished high school, so you got a 2. Brian left high school, so you got a 1. Kathy got a 3 because she finished university. And Doug and Emily, they had some kind of graduate certificate. So obviously, in this sample, Andrew is more educated than Brian, and Kathy is more educated than Andrew, right? Because these numbers do indicate ranking. However, these numbers do not tell you how much more educated Andrew is compared to Brian, and how much more educated Kathy is compared to Andrew. Let's for example, let's say, you know, Brian dropped out high school just a year before graduation. So if Brian, just continue for one more year, he would have a high school diploma. So Andrew, by successfully obtaining a high school diploma, had just one more year of education than Brian. Right? So Andrew is more educated than Brian by 1 year. However, Kathy, right, by successfully obtaining a bachelor's degree, in most cases, she would have 4 more years of education than Andrew, who only had a high school diploma. So Kathy had 4 more years of education than Andrew, and Andrew has 1 more year of education than Brian. So these degrees of differences, 4 more years of education versus 1 more year of education, were not reflected in these numbers. We only know that one person is more educated than the other. We don't know from this rank by how much. Okay, so this is a very important property of ordinal measures. We can visualize, our example in this as such using the scale, right? So in this case, the difference between the 1 and 2 is much smaller than the difference between the 2 and the 3. And we can also, can easily think of an example where the difference between a 3 and a 4 is way larger than a difference between a 2 and 3 or difference between 1 and 2. Right? For example, 4, if both Doug and Emily have PhD, that means they probably have at least 7 more years of education than Kathy. So a much wider gap here, right? So exactly because of ordinal measures, they don't have equal intervals. This is an interval, this is a second interval, a third interval. So because these intervals are not equal, computing averages for ordinal measures is not allowed. The reason is that we all know that to compute averages, we need to sum those numbers first. But because we don't have equal intervals, and you will soon notice a problem, and that problem is 1 plus 3 is not, okay, so the distance from this point to this point is not the same as the distance from this point to this point, for example. So 1 plus 3 is not the same with an ordinal measure in this case as 2 plus 4. They should be, right? 1 plus 4 is 5, and 2 plus 3 is 5. But these numbers, they have meaning in our ordinal measure. And because the intervals are not the same, this distance is not the same as this distance. So that violates the basic property of summation. And this sum does not make sense. And when sum does not make sense, averages will not make sense. Okay, so this is why ordinal measures is not meaningful to compute averages for ordinal measures. Now, if we move forward, we'll have interval measures. Interval measures essentially ordinal measures plus equal intervals. My favorite example is attitude toward marijuana use. So let's assume, and researchers make a lot of assumptions. Let's assume that this is a measure with equal intervals. So my drawing is not perfect. So if you eyeball these intervals are not the same, but let's assume they are the same. So in this case, we can say that 7 indicates a more positive attitude than a 6. Well, an ordinal measure can do the same thing, right? Because ordinal measures allow ranking. So 7 is obviously a higher rank than 6. And with interval measure, we can do the same thing. We can say, well, 7 is more positive than 6. However, because interval measures have equal intervals, we can make one more claim than we can with ordinal measures, and that is we can also, by our assumption, claim that, the difference between 7 and 6 is the same as the difference between 6 and 5 because they have equal intervals. This is equal to this interval is equal to this interval is equal to this interval, so on and so forth. So, um, and that's why we can make this claim. And that is why we can compute means for interval measures, because now 1 plus 3 is the same as 2 plus 4, and um, so on and so forth, right? And 3 plus 5 is 4 plus itself, and these equations will hold, equality will hold, because all the intervals are the same. Or 1 plus 7 is same as 2 plus 6, and 2 plus 6 is same as 3 plus 4. Again, this is because intervals are the same. Um, there's one sort of I would say a problem, but a um, one property, right, to make it sound more neutral. A property of interval measures is that its 0 point is arbitrary. It means that the 0 point of interval measures does not mean the absence of something, right? So when you say, well, I have zero money, you mean that money is absent, right? But the 0 point on an interval measure does not mean that. Instead, it is assigned purely for computational convenience. What does it mean? My favorite example is a temperature scale ranging from 0 Fahrenheit to, in this case, 60 Fahrenheit degrees. We can ask ourselves, well, what's the meaning of 0 Fahrenheit? It turns out that 0 Fahrenheit is really an arbitrary number. It is simply the lowest temperature that Mr. Fahrenheit could possibly produce by cooling brine, salt water. It could, right, by choice, have defined that temperature, right, the lowest temperature, as 10. There's no reason why he could not do that, right? But 0 somehow makes more intuitive sense if you will make that argument. So, there we go, right? 0 meaning the lowest temperature, but, we can say, why not 9? Why not 3? Why not minus 10, right? Isn't minus 10 lower than F? Lower than 0, right? So you see, this is how arbitrary 0 is. It doesn't mean the absence of temperature. It simply is given a meaning as a convenience. So that has a very important implication, which is, you can transform, this original Fahrenheit scale to a new form, to a new scale by adding 10 to each of those numbers. 0 becomes 10, 20 becomes 30, so on and so forth. Now, these two scales are very similar in the sense that, subtraction still makes a lot of sense. So you can say 20 degrees Fahrenheit is 20 degrees more than 0 degrees Fahrenheit because 20 minus 0 is 20. That makes perfect sense. And 40 degrees Fahrenheit is 20 degrees more than 20 degrees Fahrenheit. That also makes sense because 40 minus 20 is 20. But with this kind of scale, an interval scale, we cannot claim, strictly speaking, that 40 degrees Fahrenheit is twice as warm as 20 degrees Fahrenheit. And this is because, again, strictly speaking, researchers violate this principle all the time for good reasons. But strictly speaking, you cannot perform division with interval scales. You can do summation, you can do subtraction, but you cannot do division. And you also cannot do multiplication because division is simply a different form of multiplication, right? So subtraction and summation, they're allowed, but multiplication and division are not allowed. And this is why. So with this scale, you may claim that 40 degrees Fahrenheit is twice as warm as 20 degrees Fahrenheit because once you perform division, 40 divided by 20 is 2, so twice as warm. But as we said, this scale is actually equivalent to this scale because 0 is arbitrary. And if 0 is arbitrary, we can say that, well, instead of putting 0 as the lowest temperature, I define 10 as the lowest temperature, and then I add 10 to all the points that follow 10. So, the difference between 0 and 20 is 20. Well, the difference between 10 and 30 is still 20, right? The difference between 40 and 20 is 20, and the difference between 50 and 30 is still 20. So all the intervals remain the same. They're also equal across the scale. However, so this is how these two scales are equivalent, right? However, with this new scale, 50 obviously is not twice as warm as 30 because 50 divided by 30 is not 2. So therefore, right, because of this arbitrary 0 point, the division may make sense here, but the division does not make sense with an equivalent scale. So and this is why division does not make sense with interval scales. Okay. Now to fix this problem, researchers reason that okay, so then let's at least in some cases use ratio measures. So ratio measures is another step forward, and that's to give interval measures a meaningful 0. But we should bear in mind that this to give a meaningful 0 to interval measures does not always happen. It only happens for certain variables and concepts. For example, income, you can do that, right? Income is a definitely a ratio measure because it does have a true 0. Because the 0 with in income means that you don't have any money, right? The absence of money. So that's fine, right? Years of education, that's also a ratio measure because 0 means you don't have any education, formal education, right? So years of education is a ratio measure. So here income, you can say that 0 means the absence of poverty. For all ratio measures, right? 0 means the absence of poverty. Therefore, you may claim that $4 is twice as much as $2. Or you can say that you have twice as much income as I do. So with ratio measures, it's meaningful to perform summation, subtraction, multiplication, and division. So we can finally visualize the levels of measurement using this ladder. I did not come up with this idea. I borrowed this picture from the internet. So credit will go to whoever invented this ladder, which is great. So at the lowest level, we have nominal. So in this case, attributes are only named. I somehow disagree that it's the weakest measure because sometimes you have no choice. For example, in terms of biological sex, there's no other way to measure biological sex. You have to use a nominal measure. So in that sense, it's not the weakest. It's useful, right? It's just a the correct way to measure sex. One letter up, you have ordinal. So in this case, attributes can be ordered, can be ranked. That's fine. Moving up, you have interval. In this case, distance is meaningful because they're equal, right? Lastly, ratio measure has true or absolute 0 points. All right. Okay. So these are the highlights for the chapter of this week. Again, let me know if you have questions. Okay. We'll continue with the next video on our sessions. See you soon.